Welcome to this video on how to solve Ada's anagram adventure in the example language, which is Python. There's another video where I explain the two levels, and in this video I'm going to jump into solving them. So first, this was level 1 where we do the anagram check. Now I'm going to write a little bit how we can go about that. Okay, so this is the idea. For level 1, we compare if two strings are anagrams of each other. And we said we should disregard spaces and punctuation. So we remove all spaces and punctuation. Then we turn it into lowercase because we don't care if it's uppercase or lowercase letters. And then we sort them within each word, A to Z. And after that, we can just compare the two words and strings. If whatever is remaining are exactly the same strings, between string 1 and string 2 after these modifications, then we know it's an anagram. That is the idea. So now let's go to the editor and try that out. So we're going to go to this here, level 1 anagram check, and write our code. And now again I will start to write a little bit. Okay, so this is the first try. We create a new little list of strings, which is going to be too long because we're going to create it from string 1 and string 2, which we get as input to level 1. We go through them like this in Python for S in this list. And then we take our new little list here. We do strings.append. And what do we want to do? We want to remove punctuation, like we said here. So we take a regular expression. For that in Python, we import the module, regular expression module. And then we create this compiled regular expression called non-letter, re.compile. And then what do we have here? R is to create a raw string for whenever we do backslashes, which maybe it's not needed here, but it's always nice to have. Then we have the brackets, and within this we define a character set, or one character basically. And in this case, it starts with this, whatever this is called, to the power of, or up arrow, or I don't remember now. But that means the negation of whatever we put here. So A to Z capital, A to Z lowercase. Those are the letters that we want to have. And here we say that we select on each character which is not A to Z. So it's a negation. And then here we take this regular expression, non-letter, and do a substitution. So we take the string as input and we substitute any character we can find which conforms to the regular expression, and we replace it with empty string, meaning we remove all non-A to Z letters. And then I thought we'd just print that as a step in between and see where we end up. So I can press run code now. Okay, so now we can see here. So for example, we see that we got moon space starer as input, but here that space is removed, so we just get moon starer. So that is nice. We have the spaces are removed. Also in this input here we see voices rant on ... not and an exclamation mark. So we want to remove all those punctuation things. And we can see here voices rant, we have that here, and it's we have removed all characters which aren't A to Z. So far so good. So this substitution here will return those strings. We can actually do .lower here, and then we should see no more capital letters. Could also have done that before, and now we see that all uppercase letters are removed. That is nice enough. Then we can do sorted on those strings, which should yield not the words anymore, but they should be ABC sorted. And actually it turns it into lists, which is just as good. I mean, it's AEMNOO, AEMNOO, and so forth. That looks good. So now all we need to do is the last part of the plan which we had. We have now removed space and punctuation. We have turned into lowercase. We have sorted the letters A to Z. Now we want to compare those words. So basically now we don't have to print it anymore. We return strings 0 is equal to strings of 1. So that should give us 4 out of 4 in score here. And it did. So that is nice. We do find the ones which are anagrams and we reject the ones that are not anagrams. Let's see what we get. We get the false as well. They were all true this time. Okay, that's fine. So the first one is static. You always get the same test case. The other ones are random. Good. Then we go to level 2, which is the more tricky one. So now we have this basic understanding of what anagrams are, let's say. So now we want to generate it from an origin word or a set of letters in origin. So how do we do that? Let's go to the whiteboard. Here was the level 2 explanation. So we might get sandcastle in. We should return something like a list of these strings: a class tend, act unless, at class end, as I explained in the other video. So let's now go to how we can do that, and I will do some drawing here. Okay, so here we have an idea on how to solve level 2. So remember, we get the origin word in here. In this case, we use an example, a beer, like a short example. We can draw a tree here. We also get the limited word list. So, oops, that was not my idea. So we get this word list here. And it's a very limited one. In the actual exercise, we get around 1,000 words, which is not that much if you compare to what is in the English language. But in this case, to draw this tree, I'm going to use an even smaller word list of just 5 words: A, R, bar, B, and B. So I should change this color here so I can do more interesting stuff. Okay, let's see. So let's take that. So why do we use a tree? Well, this can be solved in a recursive fashion. And what I mean with recursion is when you have a self-reference, so typically a method that calls itself. And why that is kind of a nice way to solve this is because you can give the method a pretty limited task. And in this case, the task is to chop off one word which exists in the word list and then ask itself to continue from there. And as it turns out, that is a nice way to solve many problems, and it does create a kind of a tree-like structure. So I'm not going to go through maybe recursion in that much more detail for now. There are other places to look for that, but if we assume that that's an explanation enough for recursion and trees, then we look at the tree that I've drawn here. So we start at the top here, where I have written a beer. So then we have all those 5 letters with us. We look in the word list. Can we chop off any word here? Well, we have a, and an exists in a beer, so that is nice. Then we take this. So the nodes, then we are at a place where we call the function or method, the recursive one. And then on the edges here, I show which word is chopped off. And then on the node here, we see which letters are remaining. In this case, the remaining ones are beer. So going from a beer, we chop off a in this method that we're going to write. And then we have B-E-E-R remaining here. Now, if the word list had contained the word beer, then that would be nice. Then we could just say that, we chop off beer and then we have nothing remaining, meaning then we have an anagram. But unfortunately, we don't have beer. We have B and BE and BEE. So the first try is to chop off B and call ourselves. Then we have just ER remaining. that is not the word in our list. So then we have to stop there and not return anything or not add anything to our list of anagrams. It's a failure. Then we try BEE, which is a word we have, and it also exists in BEER. So then we go down here, and then we have an R remaining. And in this case, again, we don't have any word, which is just R. So far, we have failed. Then we try the next word in the word list, R, A-R-E. That also exists in a beer. So then we go down here in the tree. And now we have BE remaining. And luckily, BE is also a word in the list. So we go down there. And now we have one of those, the basic case of the, I don't remember the exact word for it, but you take a basic or base case and test that first in the recursive method. And in this case, if you get an empty input, no more remaining letters, then we know we have used up all the letters and created new words from them, meaning we have an anagram. So then we're going to add that to our list or set of anagrams and return all those at the end. And why do I say set? Well, you can do that in different ways, but we don't want to have any exact replicas, exact copies of the same anagram. So we will find here, using this tree structure, both RB and then in the other order BR. So those are not two different anagrams, they are the same anagram. And if you remember from before, we're going to sort the words within the anagram, so it's always going to be RB. So that's one way to remove duplicates. And I'm sure in this way, I mean, we're going to find more starting words here, like bar, all of them, bar, B, and BEE are all possible starting words. And I'm sure we could do something clever here to make sure we don't try the same ones over and over. But this is a very small example, so we don't need to actually be that clever. We can let it take a little bit more time, but then make sure that we don't have any duplicate anagrams. So we don't want to have the same anagram more than once. And that we can take care of by using, for example, a set is one way. So that is the idea on how to solve it. A recursive method, we go down and chop off words and see if we find full anagrams. So now let's go to the code window, and here we're going to start to implement something like what I just described. So now I'm going to write some code here. Okay, so now we have a recursive method here within our level 2 method. But okay, let's start from the beginning. We create a set of anagrams, and the reason for doing a set is, as I said, to not get duplicates, to not find the same anagram over and over again. I mean, we will do that using the current method, but at least we will only return it once. Then we had this renon letter, which was a regular expression we used before. So we start to take the origin, the word that we get as input, and we remove everything which is not A to Z, basically. So we want just A to Z to remain, and we also do everything into lowercase, is the idea. Yeah, now I remember something I have to fix here. But we have this recursive method, def recursive, and current and remaining. If we go back then to the whiteboard, what do we mean with current and remaining? Well, the current is basically the what we get as input, all the words that we have found so far. So and B will be current when we come down to here, when we call ourselves at the end here. So current are the words that we have chopped off so far as a list of words. And then remaining are these letters that we have, that I underline here, B, E, R, and ER. So those are the letters that we have remaining from the origin word after we have chopped off those letters or those words. So that is current and remaining. So if we see when we call ourselves here, current will be nothing. We have no words in the list as we start the tree. Remaining will be the words or the letters in the origin word turned into a list for easier manipulation here. Then we have a statement non-local anagrams and words, meaning maybe it's not necessary, but it's just to say that anagrams comes from outside the method and we can add to it. So we say it's non-local and words come from the input. Then we go through all those words in the word list that we have, around 1,000 words, and we try the first one, then the second one, and so forth. And the check that we do to see if we are covered by the letters in the remaining input parameter is, this is not very elegant. We could make this more elegant, but of course if it runs in time then we might be happy. So we basically go through each character in word, and then we check that remaining has at least as many as we have in our word. So if there are 2 O's in word, we need to have that also in remaining here. In exactly that example is where we do this a bit, or very inefficiently, because we will test the O. For the first O we will do this count, then for the second O we will do it again. So we would be better off by creating like dictionaries from character to number of times it occurs, number of occurrences. But okay, this is a simpler solution, less writing, and should work. And all here will mean that we need all those characters that we find to be true. The count in remaining needs to be at least as high as in the word that we're trying to add. And if we get to here, that means that was true. Then we know we can cover it. Then we will traverse the tree. If you remember, then we will kind of go downwards in the tree like this. So first we want to create copies of current and remaining, so we don't modify them in parallel in different nodes of the tree, different calls to recursive. So we want to create a new remaining. So first we create a copy of that list. That is in Python, when you do just a colon, means take from the first to the last one. It will be a copy of that list. And then we go through each character in the word and remove it from new remaining. So this copy that we just created, we remove all the characters that we have in word, so that as we see in the tree here, we always, when we have chopped off a word, like when we have chopped off R here, we go from a beer to just BE as the remaining letters. So that is what we are doing here. We remove all those characters that we have used. We also remove will fail if it doesn't exist in new remaining, but as you remember up here we check that all those letters are covered by remaining, so it should be possible. We should never get any error here. Then we just call ourselves recursively. We go one step down in the tree to a new node. We take current and add the word that we chopped off. This will actually also become a copy, which is nice. And new remaining we did a copy of before. So we'll call recursive, create a new node in the tree, kind of imaginary tree if you want. I mean, it won't be possible to kind of see it, but it is a tree. Yeah. And as we saw, we call it like this to begin with, and then we should return the sorted list of anagrams. So we take anagrams, which is a set, we turn it into a list, and then we sort it. And this means that we don't care about the case as we sort. So what Python will do is when you write key equals, is it will take the whole list and create from each item in the list a new item which it will use to sort. So it just does string.casefold that method once for each item, and it uses that for comparison instead of the original item. So for example, capital I, the word I in English is capitalized, and if we didn't do this, it would sort it in a funny way where all the capital I would go first before A. So that's why we need to do that. However, we are still missing something, and I mentioned that we want to have a base case, which is when we get down to the case where we found an anagram, where we have an empty string at the end node of the tree, then we want to check for that as well. So we need to do that if in this recursive method here. Actually, before we do any of the other stuff. So if we don't have any remaining ones, so this is also, can also say that if length of remaining is 0, it's maybe a more clear way to write it. It means we have successfully created a new anagram, or at least an anagram, new or not. And what we want to do then is we want to add it to the set that we have, anagrams.add. And here again we mentioned that we want to sort the words in the anagram. So for comparison, as you see, it's not level 1 here, but yeah, we will see it soon. We need to sort the words within the anagram. So how do we do that? We need to create a word. So we do space.join, and then we do sorted of basically current, the list of words that we have. But here as well we need to add the same thing that we had here. Key equals string.casefold. So we turn it into lowercase before sorting, or we actually don't change the list. We just use a lowercase version of the word as sorting. And then, here we do sorted list of anagrams. Let's try to run it now and see what happens. Took quite a while to run it. Okay, so we did solve it. So far everything points to, we did solve the exercise. It also goes down into more exercises as we have solved it. So sandcastle that we looked at before should return a class tend, act unless at class end with our limited word list. For example, a class dent would have been another anagram, but we don't have dent in the word list apparently. Intention was the other random test case we got. The first one will always be sandcastle. This one will be random. And then we have these ones. We have a double in 10 to, in into 10, in it no 10, in it on 10, in it 9 not. Okay, all of those different ones. We can try if we also successfully solve some other random test case. Let's see. Sandcastle we already know. Triangle, a girl 10, and art in leg. Yes, so now we feel confident that we're not just lucky, it seems to work. And this was the solution method that we used. And it can be converted, of course, to all the other languages. So good luck in solving this exercise, Ada's Anagram Adventure.